I'm Yichao from EMAS Group. Yeah, this is my dissertation talk, learning to detect geometric structures from images for 3D parsing. Okay, let's get started. So a little bit background about 3D reconstruction. So basically from sensor data like RGB images and computer algorithm, to determine what is the underlying geometry, what is the underlying shape of the scene. So 3D reconstruction has a wide range of applications: autonomous driving, AR, VR, agriculture, industrial construction, 3D printing, indoor modeling, a lot of applications. So let's see how the traditional 3D reconstruction pipeline works. So traditional 3D reconstruction pipeline requires the input of a stereo pair of images. Next, you run the feature extraction algorithm like SIFT or OBS and try to match this feature. Next, you run multi-view geometry algorithm like 8-point algorithm or bundle adjustment to determine the relatively camera pose. And finally, you triangulate each feature point to get a sparse point cloud using the camera pose. So this pipeline has been exist for more than 25 years, I would say. So nowadays, we already know that there's a lot of limitation of these pipelines. It doesn't work well on textureless objects. It doesn't model correctly when there's a reflection or transparency. So the most of feature points are not robust against the repeated patterns. Also, when the baseline becomes large enough, so this kind of structural motion or SLAM system are likely to fail. Finally, so when you have a moving object, it obviously violates this assumption. So yeah, they don't work very well. So recently, deep learning based approach becomes really popular. So from a single images, you can just use a deep neural network to predict a lot of structures just from a single images. For example, the pose estimation. So when you do the object detection, you can add another branch to predict either the three-axis direction of three-axis or bounding box. So using the fully convolutional neural network, you can do a single image depth regression. So imaging depth map out. Recently, there's also a line of work about how to predict more salient structures just from single images, like voxels, point cloud, meshes. And recently, I think this is really popular, the implicit surfaces. However, this data-driven approach has their own problem. So this is a recent research from Broden's group. So they suggest that when this kind of neural network with encoder and decoder structures does not really perform reconstruction, but they just do some kind of classification. So what they do is they design a simple baseline. Basically, they try to classify each images into they try to assign a model in the database to each images. Basically, they are doing a nearest neighbor model retrieval baseline, right? So they find that they perform almost on the same level, which means that this kind of data-driven approach is just doing some kind of retrieval, right? This is what also we expected. The reason is that unlike traditional geometry-based algorithm, this kind of data-driven approaches don't really utilize the underlying structure, at least not explicitly. Yeah. One may wonder, right, this kind of algorithm is most designed for single-view image reconstruction. So do we still have a geometric constraint on single view? The answer is obviously yes. So this is because we live in a structural world. So, and the structural world is man-made, and man-made environment are rich of structural regularities. So let's say you just look at your table, right? Your home. So they are composed with straight lines, smooth curve. Lines are tended to parallel with each other, and some are made orthogonal to each other. And there's a lot of symmetries around your desk. Your keyboard, your monitor, your cell phone, right? They're all symmetric. So the problem is, how can we detect them reliably and utilize them for us to understand the 3D world. Yeah, so here's the main topic of my thesis. So I'd like to ask the following question. How could we incorporate the geometric knowledge into data-driven approaches? So to this end, I identified 4 important components that is the key aspect for an algorithm to work. So they are data representation, end-to-end learning, geometric structure, and correspondence. So to this end, so here's a series of lines of work that's trying to push the frontier of this kind of structural-based 3D parsing or 3D understanding thing. So I will talk about our first, the initial efforts, the learning to reconstruct wireframe from single images. This is published in ICCV 2019. So the problem is try to solve is the data representation. So let's take about what's the traditional data representation we use for 3D reconstruction. Obviously, point cloud, right? So the problem of the point cloud is that they are often not ideally for storing, sharing, and interacting. So to give an example, so the left figure is gear wheel skinned by a professional 3D skinner. So the problem here is that it is really hard for an engineer to directly edit this kind of point cloud reconstruction. So they need to manually convert it into maybe a high-level representation like a CAD model, maybe in the SolidWorks. On the right-hand side, we show LiDAR street skin using a commercial Viadan LiDAR. So the problem here is that it is just very hard to determine the semantic information. Actually, up to today, most of the information, semantic information, are still predicted from mostly from the image. Right? So maybe we can get some intuition from architects. So when architects try to design building, what they do is they first draw the CAD model either on a paper or on a computer, right? Computer-aided design model. So this kind of model are highly structured. So basically, they are composed of junctions, sharp corner, and straight lines, and the planes, smooth curve. Maybe we can just try to predict our reconstruction results using the similar format. So this inspires us this work. So basically, wireframe-based 3D reconstruction. So wireframe basically, mathematically, it is a graph. Right? For each vertex, we try to store its pixel coordinate, steps, and its junction type. So in this work, we mainly focusing on 2 types of junctions, the C-type junction and the T-type junction. So basically, the T is a T junction. So you have a background line that is occluded by a foreground plane. So you have a T junction. For the rest of junctions, we just assign it to C. There's other types of junction if you have more assumption, but we just consider this in this work. So with this, if we can reliably detect wireframe, then it's easy to do some AR/VR application. You can easily detect all the planes from images and maybe add the logo to the building, right? This is a work when I was done in Adobe. So we put an Adobe logo to the images. How do we do that? Yeah, so since this is initial work, so what we basically is apply a 2-stage algorithm. First, we from a single image, we use a neural network to predict a series of intermediate representation of the 3D wireframe. They are depth maps, junction heat maps, edge maps, and the vanishing point. Of course, you can get vanishing point from other approaches. Yeah, so then from the junction heat map and the edge map, we can try to vectorize these lines from the heat map. Then we can use this 3D depth map and the vanishing point to lift the vanishing point lifted the wireframe into regular 3D representation. So let's just see a demo. So from single images, we predict 3 heat maps. Then we vectorize the C junction heat map and the T junction heat map by just doing thresholding on them. Next, we have a line heat map. So basically, you can check whether there's a line connect between every pair of junction from the line heat map. Then you can get a 2D wireframe. Next, we have a vanishing point. For those who are not very familiar with vanishing point, basically a vanishing point is every parallel line will intersect at a vanishing point. So it will tell you what is the direction of the lines relative to the camera. So it's a very strong prior from a single image you can get. And we also have a depth map. We need a depth map because there will be some ambiguity if we just rely on vanishing points. Then we form a convex optimization problem. We solve this problem to optimize the depth for each junction. So you can get a very nice, clean wireframe representation. So you can use your mouse to rotate to visualize them. Yeah, so there's a big, here's a wireframe reconstruction result for the famous Big Bang clock. Yeah, I will skip this. Here's more result. So yeah, from a 2D wireframe, we can extract the ground truth 3D and the inferred 3D. You can compare them. Once the algorithm, if the algorithm doesn't fail, you can see that the result is almost identical to the training data. Yeah, this is because everything is regulated by the geometry principle, the vanishing point, and the lines in this case. Okay, that's basically concludes the first work. So at the end of this work, so I want to talk about the failure cases. So in this work, I think the most two common failure case is the vanishing point. Either you can use a neural network to predict vanishing point, or you can use some kind of traditional algorithm to get them. The vanishing point is not always accurate. So I will talk about this later on, but you can see that once the vanishing point is wrong, all the line will be oriented to the wrong direction. And second is the line detection is a very challenging one. So here the problem is once the line are short or dense, if the heat map based method, it's just very hard to get the line extracted because you can see the resolution is just not high enough, and it's just not really easy to increase the resolution with the current neural net technology. So this inspires to our second work, the end-to-end wireframe parsing. So what we are going to do is mainly to solve the 2D line detection problem or wireframe detection problem. So with the end-to-end learning principle. So some background. So previously, as I mentioned, not only my work, but all the previous line detector, I think prior to this work, it all follows some kind of two-stage algorithm. The first stage, you try to filter the images. So by converting the RGB images into a line heat map. So traditionally, you can do things like canny edge detection. Modern days, you can use neural network to do that. The second stage, you want to run a heuristic algorithm to turn this heat map into vectorized lines. This is I think prior to this work, everyone used this pipeline, this two-stage pipeline. So the problem is, especially on the second stage, you want to search the heat map and turn it into a vectorized junction and lines. This implementation will be relatively difficult. I know this because I do implement that. There's a lot of hyperparameters you need to tune, so the performance is often not so good. And because the heat map is not always perfect, right, from neural network. So the goal will be, hopefully, we don't need a two-stage algorithm. We don't want any heuristic algorithm here. So just an end-to-end trainable neural network to detect lines. We hope we can directly output vectorize the wireframe, including line and junctions. It should be easy to implement, not to deal with a lot of C++ code to extract all the lines, just like previous people did. Also, it should yield just state-of-the-art performance. Okay, so here is basically a simple pipeline of our new method. I will go through the one component by one component. So first we have a backbone network. Basically, it's common known as a feature detector. So you turn an image into a feature map. Next, you try to turn this feature map into a junction heat map. Basically, you do another convolution and try to predict add the supervision to this heat map and just try to predict the junction heat map. So there will be supervision during training on this heat map. So we still use a junction heat map because junction heat map is easy to process. You want to vectorize it, you just need to do a thresholding or a non-maximum suppression on it. So after you have the junction heat map, you try to sample some lines from junctions, right? So the most easiest way is you just connect every pair of junctions to form the line proposal. Finally, with the line proposal, you just we do something very similar to the ROI pooling. If you are familiar with the literature of object detection, we do the LOI pooling, the line of interest pooling. So basically, the idea here is that for each line, we sample several points, let's say 64 points along the line, and just concat their feature together and use a neural network to classify whether this line is a valid line or not. So it's very similar to the previous object detection pipeline. So by using this so the benefits obviously is that everything is handled by neural network. So we no longer have some heuristic line search neural network. The line search algorithm. So the benefit is obviously you get a huge performance improvement. So LSD is the line segment detector, the traditional one. AFM and the wireframe is the previous neural network-based line detector. They're also two-stage. So you can see our LCN is generating much more clean result compared to their algorithm. This is because our algorithm is really end-to-end. So it's so you don't need to write any most of heuristic code for it. Yeah, this is another example. I want to mention that if you look at the chair, right, even the ground truth, don't label that because it's the contrast is so low, while our algorithm can get most the lines out of the chair. Also, yeah, the wireframe is just more clean than all the previous two-stage algorithm. Yeah, so result on the number, this is a really huge improvement. If you consider the structure correctness, if you consider the connection, the correctness of connection, then we have almost 14 points SAP improvement. If we use a more traditional, just plot every line to a heat map, then we still have a 50 points FAP in the improvement over the previous state-of-the-art method. Yeah, this is I would say is a huge improvement. In this year, we also do follow-up work. Basically, I think the important thing about the LCN, the previous work, is we identify that the problem of line detection is very similar to the object detection, right? Hence, you can use most object method in the object detection onto the line extraction. So here, we do a single stage wireframe parsing. So basically, we use things very similar to the SSD and YOLO. So we just predict several heat map and try to assemble it into a wireframe. So we get a similar performance, but the inference time will be much quicker. Yeah, that concludes the line. Things about the lines. So for the initial work, we also has a problem on vanishing point, right? So previous vanishing point algorithm is not good enough. So that's motivated us so that we can working on with a more advanced vanishing point detection algorithm. So to detect more geometric structures from images. So a little bit introduction about vanishing point. So on the vanishing point are basically parallel lines in 3D. So when they project to the photo, so they will intersect the same point, what we call the vanishing point. Vanishing point is important because they are one-to-one map between the line direction and the coordinate on 2D images. So basically, once you can detect the vanishing point, you know the line direction in the camera space. So how do we detect vanishing point? So we also have a traditional approach and a neural network-based approach. So traditional approach, it's still a two-stage algorithm. We first extract lines, and then we cluster a line based on their endpoints. This kind of algorithm is really accurate because, well, it's a geometric-based algorithm, so you know you're calculating based on the their lines intersection, and the lines are relatively accurate. You have a lot of lines, you can average them together, so it's super accurate. The problem here is that there's outlier, so there's outlier lines. If there's too many outlier lines, your algorithm will likely to fail. This is especially the case in, let's say, the things that are not cherry-picked, right? You just take indoor images, then more than likely your thing don't have super regular lines, and there's a lot of outliers. Neural network-based method, you can do is you can either just regress the coordinate for the vanishing point, or you can say you divided the image into a lot of patches and you do a end-to-end classification, which patch has a vanishing point inside it. Both of them are kind of robust because they are learning from data. The problem is it's a neural network, so it don't really understand the definition of vanishing point. So they are inaccurate. So here is an experiment to demonstrate that. So this is the error plot for two algorithms, the LSD. So I mentioned this line segment detector. You can use it with line cluster algorithm like J-linkage. You can get the vanishing point. Also, we have a CNN regression. We just put a regression baseline for it. So the x-axis of this plot is the error. So vanishing point is corresponding to the 3D vector. So we use the angle difference as the error metric. The y-axis says what's the percentage of data we can achieve this error. So the left figure is basically a zoom-in version. So we just take a look at 0 to 2 degree, while the right figure shows the 0 to 45 degree. So the things here I want to show you is that the geometric-based algorithm, traditional one, the LSD plus J-linkage, is very accurate. So the median error is something like 0.2 degree, or you can imagine 0.2 degree. You can even not find it. You can definitely not distinguish it on the picture. However, it's kind of not as reliable as a convolutional neural network. If you just relax the angle difference to things like 10 degrees, you can find that the CNN definitely get more images correct. So actually, there's a cross point around the 3 degree. So this inspires us, right? So we want an algorithm that is both accurate and robust. Also, we hope, just like previous lesson we learned, we hope the algorithm is end-to-end trainable. So that to this end, just like previously we have LOI pooling, we also want a new operator that can capture this kind of geometry cues. We obviously want an elegant algorithm, not things like heuristic. So we want to have a very elegant, simple to implement operator, so you can help people use it. To this end, so we propose things called a conic convolution. So conic convolution. So the idea here is that we show the traditional convolution on the right figure images, and the conic convolution on the left figures. So conic convolution requires a vanishing point candidate, or we call the convolution center, as the input. So basically, the idea is that we always rotate the convolution kernel with respect to this convolution center. Why do we want to do this? This figure shows some intuition. So if your candidate position of the vanishing point is correct, then this convolution filter can serve as a line detector. Because, well, if this point is a vanishing point, then there'll be a lot of lines that point toward this point, right? So this filter can serve as a line detector. It will generate a very strong response about it. On the other hand, if the vanishing point is not correct, once you do this kind of convolution, and the response will not be as strong. So hopefully, later stage of a neural network can pick this difference up and tell whether this vanishing point is good or not. There are several details we need to work out because due to use classification rather than the regression pipeline. So basically, we need to try to enumerate vanishing points and feed it into a neural network, and with this kind of conic convolution neural network. Two problems. So we need to sample it and test it. How do we sample vanishing point? This is not really something new. Basically, every vanishing point corresponds to a direction in 3D. So we can just put the image onto a sphere. Traditionally, this is called a Gaussian sphere. And you can just sample the unit vector from this sphere. It's equivalent to sample on the image space. For the inference, you want it to be relatively fast. So you need a hierarchical inference, cost to fine inference. So initially, you first sample the vanishing point in a cost grid, and then you refine it from the previously best vanishing point and refine it again. So you can quickly pinpoint what's the best vanishing point. Yeah, so we tested on both synthetic dataset and the real world dataset. Synthetic has a more clear definition because every vanishing point is clear. So it's a kind of ablation study. So on the synthetic dataset, we are able to achieve the limitation of a floating point number. So basically, we are get something median error around the 0.1 degree. If you take the cosine value, it will be just around the epsilon of float 32. I think this is amazingly good. Consider normally you won't get machine accuracy on any algorithm. So compared to the previous algorithm, our curve is just much higher. So either the LSD and the traditional just the brute force regression. And you can see the brute force regression cannot beat the LSD, the traditional geometric-based approach, when on the left curve, the curve between 0 to 1 degree. So, but when you combine the geometry, you can beat both the learning-based approach and the pure geometry-based approach. Yeah, our algorithm also works on the natural thing dataset. This kind of dataset is more, I would say, there's more noise in the dataset because the vanishing point usually is not that clearly well defined. There's distortion in the images, and sometimes it's just not well defined. But our curves, the median error is around less than 1 degree, still amazingly good compared to previous traditional approach and the deep learning based approach. Good. So this year we also have an extension. So to make this fast, we may wonder that this kind of cost to fine inference might be slow, right? So a little bit with some effort, you can make it faster. So we have a traditional convolution backbone. We have confidence. So we use efficient conical conv, and to get the confidence map on the sphere, we do an NMS and get the vanishing point out. Finally, we use the idea like learning to optimize. just like a cascade CNN and let's say even the ResNet, right? So you use a neural network to refine the vanishing point quickly using this kind of residual block. And you can achieve that almost in real time, 330 FPS, no problem on single GPU. Yeah, another extension of the conic convolution is what we call the homographic convolution. So instead of driven by a single vanishing point, you can let it driven by 2 vanishing points. So that's basically a plane, the horizontal plane. So by using the homographic convolution, you can use it to do the normal estimation. It's not more like a dense normal map estimation. To get it more accurate, we also submitted this work to CVPR 2021. That basically concludes the things about the vanishing point and conic convolution. One thing you may want to ask is, vanishing point sounds like the research people done in 1980s. So it's probably not that popular recently. So why, could we do some more practical with structure-based learning? Yeah, the answer is obviously true, things I mentioned here. So let's take a look about the problem of single view post-estimation. I think this is really popular recently due to the autonomous driving things, right? So from a single images, we want to get every object out, and they are 3D bounding box. Basically, this is most autonomous driving startups currently doing. The problem here is that this problem is not that well defined. So more often, the single view post-estimation problem is defined by the data set rather than by a particular rule. So how do you define what is this bounding box, right? You ask a human to label it, and you put it in a data set. So the problem is defined by the data. So how do you solve it? Of course, you use a data-driven approach, like convolutional neural network, mask CNN, things like that. Right? You add a branch to predict the bounding boxes from image patches. So could you make this problem more well-defined with more like geometric principles? Because if you want to solve it with geometric approach, you need to define it in the language of geometry. Right? So this is too fancy. So let's just take our single images. And we don't want to predict the bounding box. That's also too fancy. Maybe we just want to predict the 3 principal axes for the bounding box. Okay, we just simplify the problem a little bit, assume that everything is segmented out, and you just want to predict these 3 principal axes. One problem is how these 3 principal axes is defined. Let's say on a dataset like ShapeNet, Pixel 3D, how do you define it? Actually, if you read their paper, these axes are defined by the symmetry plane. So on ShapeNet, they explicitly mention that we align every object so that the x-axis will be the normal of the principal symmetry plane. So the idea here is that basically the single view post-estimation problem is to say how do we detect the normal of its symmetry plane. Then this problem is becomes much more clean, right? So it's a more well-defined problem with in the language of geometry. So how do we detect the symmetry plane, the normal of symmetry plane, with a single image? One thing I want to mention is that this problem is actually somehow equivalent to the vanishing point detection. How to see that? Basically, you just connect all the pair of corresponding points, and these lines are parallel in 3D. So after perspective projection, this line will intersect at a vanishing point, maybe at the infinity. So this problem is extremely similar to the vanishing point detection problem. Of course, there are things different. So I will mention that later. So how do we do that? So once you know that there are things like a vanishing point in the images for the symmetry. So for each pixel, we can draw a line, connect this pixel and the the vanishing point, right? So what we know is that its corresponding point must be on this line if the normal or the vanishing point is good. So basically, the idea is that we need to, for each image, we need to search along this line and check if we can find a corresponding point on this line or not. Actually, the process of search this corresponding point, it is equivalently to say we need to determine the depth of this pixel. If you are familiar with multi-view stereosys, you shouldn't be very familiar with this kind of cost volume structure. The idea is that for each pixel, we need to predict, right? Assemble a cost volume for the neural network so that it can predict whether it can find a corresponding point on a line. So if this is a correct line, it's correct vanishing point, then we can find if this is a correct symmetry normal, then we can find the correspondence for each pixel, for most pixels at least, right? So if it's not, then it says incorrect surface symmetry normal, then we cannot find it for most of pixel. After we constitute this cost volume, we can just use the more neural network to regress the result. So the pipeline is kind of complex. I won't go through it, but you should know this idea, right? Basically, we enumerate the symmetry normal and we classify using the idea illustrated above. So we tested on both real-world dataset and synthetic dataset. So basically, what you expect, you can expect a similar result, just like the vanishing point detection algorithm. So you will get much more accurate results after you add the geometric principle. So the medium error, according to our test, the previous best algorithm can yield accurate medium error around 1 degree. But once you get the geometry correct, you can make the error go down to 0.3 degree. So the median error. So the average is you can still improve that. It's not that obvious because the average error is dominated by the outlier. Still smaller than 0.5, our algorithm can have 65% of data achieve this error, while traditionally you can only get less than 20% of the testing case. Yeah, this is the Pixel 3D and ShapeNet result. Yeah, that's basically conclude most of my work related to the method for structure-based 3D parsing and understanding. One thing I want to mention is these methods are all data-driven approaches. Also, we apply the geometry into it. They are still supervised learning algorithm. Supervised learning algorithm requires data to train. So when I'm working on these things, one thing I find kind of frustrated is we don't have a good data set. So sometimes you work on the synthetic data set, which is always not convincing enough. That's why later on, so I collect on my own data set, the data platform called the Holy City, to help the future research regarding the structure-based 3D understanding researches. So let's see what kind of requirement this data set need. First of all, it should be real world. Synthetic is boring, right? You don't want synthetic data set. Next, we hope that the images are general enough. So I think the problem previous people often have is that they often just use a very specialized thing, like the thing obviously has a vanishing point, very clear vanishing point. But like say a random image on the internet isn't so obvious. So we hope that dataset is general enough. Finally, we need to have a structural annotation like wireframe, plane, symmetry, vanishing points. Traditionally, the most 3D dataset only has point cloud because you can collect point cloud with LiDAR. Or if you just use things like structural motion, like a CoMap, you get still point cloud kind of crappy. Right? what we really hope is something more advanced, like a structure-based annotation. We hope that the plane and the wireframe is directly provided by the dataset rather than we need to post-process the point cloud to get them, which is always not accurate. So this is how I this is my solution to this problem, what we call the Holy City, a city-scale data platform for learning holistic 3D structure. So yeah, get the training data. So it's probably the most important things for AI. So this is our data set. So we have two parts, the CAD model and the paranormal images. So we collect the CAD model of the London city. So according to the provider, this CAD model is accurate to 50 centimeters of accuracy. This is really good if you consider it's in an urban environment. So we also have paranormal images, the images from Google Images. So you can collect as many as paranormal images on Google. And we do the alignment work. So basically for each images, we can overlap it with the underlying geometry. Therefore, you can easily extract the planes, lines. And of course, you have a plane, you have the lines, then you have the CAD model. So you have a depth map, you have basically you have a lot of extra structural annotation that you can use later on just by writing some geometry processing code. Yeah, so this can be very powerful. So semantic information, we also have it. Depth, normal, vanishing point, no problem. Yeah, so here's some brief comparison. The table is huge, so I won't go through this table in details, but just let you like to know that we have it. So yeah, so the plane. So we can also test some algorithm on this data set. Previously, if you want to do the outdoor normal estimation or outdoor plane detection, it's kind of frustrating. There's really no ideal data set for these tasks. What you can do is you can either do the transfer learning, so you train the data on other data set, or you can train the data on a synthetic data set. So we do the comparison to say that actually you prepare outdoor data set is much more helpful. So hopefully I answers these questions. How could we incorporate geometric knowledge into data-driven approaches, right? So through the 4 bullet point, data representation, you want a good representation, like a wireframe, and it's more compact. You want to apply the geometric principle, so the geometric structure, like lines, vanishing point, symmetry, into your pipeline. Also, traditionally, we don't use learning, so learning is important because it just removes most of the outlier for your algorithm using the data, right? Finally, we want to exploit the correspondence. So single view, we have symmetry, multi-view. I think this is already been done a lot of times. Finally, we have a data set. You need to put everything together with a data set. So that basically concludes this work. So for anyone who is interested in the more structure-based 3D reconstruction and understanding, I would suggest you can take a look at these resources. So there's an ECCV workshop on holistic structure for 3D vision, and there's an awesome holistic 3D link for you. Also, we have a reference. This is most of my publication along this line of research. Yeah, finally, acknowledgement. I would like to thank my advisor, Professor Imar. So for his advice during my PhD study. Without him, I think I want to be here. I'd also like to thank my thesis committee, Professor Jitendra Malik, Professor Sarah McLean, and Professor Yasutaka Furukawa. And thanks for your time for being my talk. Finally, I need to thank my collaborator and former and current group member and my advisor in different institutes. So you definitely provided me a lot of help in my PhD research. So thanks for my some sponsors, and thank everyone for listening. So that's I will answer your questions if there's any. Thank you.
All right. Yeah. Thanks, Yichao, for a very good talk. And also, I think it's time to take some questions from the committee or from the audience. Maybe you can start or?
Yes, I can start. Yichao, thanks again for that great talk. Really fantastic line of work. And in particular, I found the symmetry one very interesting. I remember the symmetry talk could be a lecture in computer vision class, which he gave to us when I was at UIUC as a student back then. You're one of the people who thought through symmetry regularity deeply. Since due to time, limit to one question and also maybe hard discussion. So data representation. So when you think about geometry, there are like corners, edges, junction, maybe surfaces, volumes, or if you go for CAD, BREP or BIM, something more higher order, complicated, and you are more working at the level of, to me, junctions. So there are like many more layers ahead. And if you look at the results, pretty impressive, but still from our perception, how we perceive, there seems to be a big gap to me. Still we are far behind what we can do. So if you agree, I wonder what is the weakness of your current approach? What that has to happen to make this result more close to our human perception quality?
Yes, I totally agree with your points. So basically, currently what we can do, this kind of CAD level presentation is kind of still limited. So we can only detect junctions and the lines. But in real world, people use BREP representation, boundary representation for the CAD model. I think there's two ways I will imagine that we can solve it. So first is, I think more in the short term. So if you want to do things like interactive editing, right? So basically, if you take a figure, use a computer algorithm to reconstruct that, then maybe a human can fix the rest of things for you. So if the computer algorithm cannot do that. The second one is to add the more structures into the pipeline, like curves, boundary, planes, to the extent that there will be splines and boundary representations. So so that's I think it's more like future researches. I think one bottleneck here is a data set. We really do not have a very good data set on a large scale with a good high quality CAD representation. I think most of currently CAD models are still just too toy from my perspective.
Yeah, thanks. And I have all my answer to my own question. And this is what I think. And I want you to actually discuss now for a little bit. So to me, so the higher order geometric reasoning, how junctions should be formed, how they should form maybe surface, how they should form a volume. So these things, how to reason, it's very difficult. There are two ways right now. One way is to redo local geometry detection by deep network. A higher level reasoning is difficult. So maybe do optimization. Combinatorial optimization, you go for optimization. It's slow, but that's something. That's one way. The other way is to just make everything end to end. This is, it might be your approach. Make everything end to end. And since the ground truth has such information, how all things should be put together, hopefully end-to-end learning somehow make it a low-level geometry detection selection work. But to me, that's an issue. So you can just make end-to-end. The hope that you somehow learn, because these higher level things are in ground truth data, the supervision should make it happen. To me, that's difficult. So you have to really change representation in your architecture. again, the kind of putting the low level, put things together end to end. Hope that the higher level thing happen by backpropagation. That maybe be an issue. So somehow I feel that the issue is not that data set. The issue is the representation in architecture.
Mm-hmm. Yeah,
I wonder if you agree on like this thought.
Yeah, I mean, once you go to more complex representation, so then I totally agree that the representation is also a huge problem after you project a complex 3D structure onto 2D. So it's really hard. There's just too many cases you can solve. But I think there's still hope. I mean, yeah, with careful consideration and classification, you divide them into different categories, you can still solve it. So I think with good data set and a good approach.
Yeah.
So,
sorry.
Yeah, just to follow up with a quick comment, right? So currently, I think I agree. And if you have simpler structures and end-to-end, as a modular, it makes sense. But once you have more complicated relationships, structures, lines, surfaces, and also structure symmetry, and more complex, then there should be a corresponding architecture to the representation you are seeking, right? To reflect the relationships of all those components you are trying to detect or train to detect, so on. So that I think it's really still at this point, I think you have done work, that's what, floor plan, for example, right? Really requires putting more components together. So that, again, the representation probably will stipulate what the corresponding architecture would be, right? Definitely this, it opens up all kinds of possibilities, to how to put all the things together to form very, very complex 3D high level geometry, right? That's actually the exciting part for the future. Yeah, good.
Yeah, thank you. Yes. So, given time, that's all from me.
Yes, guys. We can take also, or else you can continue, and also can also open the floor to question to some of the people in the audience.
Yeah. Any questions? Welcome.
May I ask a question? Hi.
Sure.
This is Boubacar. So I'm from the department, so I'm in physical electronics, so I'm more interested in optics. Can you hear me?
Yeah, I can hear you.
Yeah, so I just came here out of curiosity. So I found your talk actually very interesting, and I learned quite a bit. So in particular, your data representation now, you discuss these wireframe, etc. So, but my question is, wireframes is basically using geometry as in a flat space, right? So you have points and you connect those points. So yes. How much resource does it take for you to come up with the wireframe representation of an image, for instance? And I was wondering, because there are ways to directly detect these lines, let's say in hardware, in optics, for instance, with some special lenses, you can do that directly. So how much resource does it take? So that's my first question. And the second question is, maybe if we go beyond the wireframe, is it possible to introduce curvature in the representation of the object? Instead of having, let's say, a flat space, which is basically a Euclidean space, use a representation in curved space, so that you can add more information to the representation. So is that possible? So that's my second question.
Yeah, thanks, Boubacar, for your questions. So the first question is how many resources does it take for the wireframe representation? I think there's a multiple direction I can answer these questions. So first of all, the wireframe represented itself is extremely compact. You only need to store in the endpoint and the connectivity between this endpoint as your representation. So the representation itself is compact and requires almost no resources. But the problem is that you probably want to ask us how much computational resources it needed to infer that, and how much resource do you need to take to annotate, let's say, a data set. Mm-hmm. On this hand, then I think this is probably the shortcoming of the wireframe. It takes normally you have two ways to annotate the wireframe of a dataset. You can do it in the 2D or you can do it in 3D. For 2D, basically you just click the point on the images to label the wireframe. On 3D, you need like something like a CAD model representation with very sophisticated computational geometry algorithm to project it back to the image space. So this kind of things I think is currently lacking. So hope my dataset Holy City can some kind of alleviate this problem. So yeah, for the second questions regarding the curved representation, I think that this is can be a relatively straightforward extension for the end-to-end wireframe parsing. So in the graphics side, so there's currently we already have a very good representation of the curves, B-splines, and the nervous curve. Right? So the only thing I think we lack is how do we assemble these into a neural network, and how can we prepare a data set for this kind of things. So I think that probably data set is probably time-wise is more time-consuming for that to get a good data set with all the curve label.
So you didn't put this. I think you had slides before, right? So how much effort actually went into preparing the data versus how much actually you're coding the.
So
I think you have a slide sort of suggesting.
The left up corner. Right? So the idea is that just get the training data ready. Probably is the most time-consuming part for the wireframe-based 3D construction.
Yeah. So, but once you learn the system, as you can see that you have enough data to train the data on the scene, then the inference part can be very, very efficient. Now things they are already pushing things into a frame rate and with a little bit of engineering. But again, the question is, we probably by now we understand the generalizability of the trained neural networks is very as good as the data provided to it, right? Mm-hmm. So if you wanted to apply to new scenes, again, new data is required, or at least the amount. And there's actually back to Yasu's question early on, right? There will be a limit of this end-to-end design. Maybe for a simpler structure is good. But even from a practical point of view, right, end-to-end might have an issue is that you lack generalizability. If you really say for the whole complicated system inference, even you have the data, you trained it. But the question is, what if the model is not reusable, components of it is not reusable, then once the task is changed, you still have to go through the horrendous process of preparing new data to retrain the model, right? So I think there will be really a good balance is that the geometry representation should really help to people in the future to design a more modular learning system or training systems so that you can best use the information you have learned in data, maybe some of the low-level things, right, can be much more easily generalizable rather than the high-level tasks. So those are the things really open up all kinds of issues, which I think is not currently well understood in the deep learning or even geometry based approach, right? We are still at a relatively lower level, dealing with lower level structures and features, right? How to assemble those together. I think maybe even borrow ideas from graphics or from architecture. So that's really is needed, right?
Yeah, thanks. Are there any other questions?
Yeah, any other student have any questions? I think we're a little bit running, a little bit over time, but we can have maybe one more questions.
No, okay. I have one last question, more general. So I believe in supervised learning so far. the other part of computer vision, no supervised learning. Self-supervised or weakly supervised. That's a kind of big thing. But so far in 3D vision, we do not go there much. To me, supervised learning, that's I really believe the best way. I wonder, why do you think we are not so much into non-supervised methods? Have you thought about non-supervised or weakly supervised? So far, my impression is you have to solve it. Yes, get all the supervision, annotate, then go supervised learning. Do you kind of believe that's the way to go, or have you thought about a different way? No annotations, a weaker annotation. Do you see future in those methods?
Yes, I definitely agree with that. In fact, currently I think there's I think supervised learning and semi-supervised learning in the 3D context is kind of there's many kind of definition you can say. So in the multi-view cases, we already have a lot of semi-supervised method or halfway supervised method. Basically, like single view depth estimation. You don't need to have a depth annotation. Just you can supervise it from a video by using multi-view correspondence. You don't need a depth annotation per frame to do that. On the other hand, we also have things like a point feature, like a deep learning based feature descriptor. You don't need to label each feature point on the images. They are kind of already fall into the unsupervised regime. For things like lines, vanishing point, and symmetry, I do believe there's some kind of clever way you can put them into an unsupervised framework. Given that you have a stereo pair or more view as input to the images, I do believe that. That's it. But if you are talking about single view, then I think it will be very hard to do.
Yeah, thanks.
Yeah.
Thank you.
So just again, I think if you have multi-view or even with a 3D image and the 3D model, CAD model, there's a lot of, you can actually really open up all kind of interesting, rich scenario of semi-supervised or weakly supervised settings, right? You have a 3D, but you don't have to, maybe not the perfect alignment of 2D, 3D. Then that actually some of the techniques from some semi-supervised learning can really helps, right? Establishing certain correspondence between the CAD model and the images. That I think is another avenue. Currently, right now, even the alignment and also labeling is still very tenuous. Still, right? I think you hire companies or take a long time to get those things right. Also, you still have to do refinement and so on. So that pipeline really can use a lot of help from autonomous or semi-autonomous systems to just get the data ready and so on, right? Or multi-view traditionally has been really correspondence is self-supervised. You can think about it. But again, how to use that more efficiently in the learning setting, I think that has not been so well explored in the traditional structure for motion or bundle adjustment, right? So I think there's opens up all kinds of interesting opportunities, right? Especially now 3D gets become one of the truly kind of bottleneck for AR, VR, for autonomous driving, for digitizing of the digitization of the cities and all the interactions and robotics as well, right? So I think that put all these issues become more and more important and present. Yeah. All right, good. Thanks. I think that's about time we have. Thanks everybody for coming, and thanks Yichao for a very good talk. And I think you should get your thesis ready, and hopefully that the committee will agree. Okay. Thanks, Yasu, and thanks to the rest of you. Bye.
Bye. Thank you.